My name is Julian. I'm a PhD student in the ABS lab at CU Boulder, and today I'm presenting some of the work we've done on using a pulsed electron beam for electric potential sensing and control. So our lab has done quite some work on remotely estimating the electric potential of a nearby space object, such as a neighboring spacecraft, for example. And both of these, so we've worked on two methods, and both of these are based on emitting an electron beam from a surfacing spacecraft and aiming that electron beam at the target spacecraft. As the electrons from the electron beam impact on the target object, they give us information about the electric potential. And this is basically summarized by, first of all, the electrons excite the emission of secondary electrons from the target object. And these secondary electrons are accelerated towards the surfacing satellite, and by measuring the kinetic energy of the secondary electrons as they arrive at the surfacer, we can estimate the electric potential of the target object. Now, at the same time, the incoming electrons from the electron beam excite the emission of X-rays from the target object. And again, that those X-rays give us information about the electric potential. So by using an X-ray detector to find the maximum energy of the emitted X-ray photons, we can also get some information about the electric potential, which is the X-ray method. I really went over this really quickly here, but if you're more interested in these methods, there are a lot of presentation videos and also conference papers and journal papers that have been published in our lab about these two estimation methods. Now, there are some challenges with these estimation methods, and that is that the incoming electron beam charges the target object. Now, we want to measure the electric potential of the target object without significantly perturbing it. So if we're interested in the natural potential, so without the electron beam current, then any impacting electron beam will perturb the electric potential, but we're interested in the potential without those perturbations. So in the end, we're interested in minimizing those perturbations, and that's one of the challenges. Now, the other challenge is that we have some limitations on the electron beam parameters for the remote sensing methods. So, for example, the electron method prefers a low impact energy or landing energy of the electron beam because the secondary electron yield, so the number of secondary electrons that are excited, is higher for lower landing energies in the range of less than 1 keV up to maybe 2 or 3 keV. That's shown in the figure on the top right. So with a very high landing energy, there are actually less secondary electrons being emitted, but we want to emit as many electrons as possible or excite as many secondary electrons as possible, because that will give us a stronger signal for the secondary electron method. Now, on the other hand, the X-ray method benefits from a high impact energy, and that's because as we show in the figure on the bottom right, there are several characteristic X-ray peaks in the X-ray spectrum. But for higher landing energies, we're actually getting away from these characteristic peaks that might interfere with our estimation methods. And also, the higher the landing energy of the electron beam, the more elements we can characterize in the surface material that we're hitting with the electron beam. Now, both methods generally benefit from a high electron beam current because this will result in a higher signal, which is generally better for estimating the potential. Now, in the following simulations, I consider the plasma electron current and the resulting secondary and backscatter electron current due to the ambient electrons. Also, I'm considering the plasma ion current, and similarly to the electrons, the ions that are impacting on the surface of the spacecraft excite the secondary electron emission due to the ion impact. The final naturally occurring current in the space environment is the photoelectric current due to the sun, which I'm also considering here. And the charging model that I'm using here assumes fully conducting spacecraft, so the entire spacecraft is charged to one single electric potential. Now, because we're using the electron beam, we also have to consider the electron beam induced currents. The electron beam induced current on the target is negative because we bring negatively charged electrons to the target. But at the same time, these electrons again excite secondary and backscatter electrons that provide a positive current on the target spacecraft. For the servicer, the emission of the electron beam results in a positive current on the servicer due to the emission of negative charge. Now, one important point here is that the electron beam can only reach the target if the initial energy of the electron beam is greater than the electric potential difference. Otherwise, if it's smaller than the electric potential difference, then the beam is not energetic enough to reach the target, and it might actually come back to the servicer, resulting in a net zero electron beam current on both the target and the servicer. Now, some assumptions for the following simulations are that, first of all, the target object is eclipsed. Second, the servicer potential is assumed to be controlled and maintained at a potential of 0. So the service is essentially neutral. That just simplifies a lot of the results that we show here. And the plasma conditions correspond to a geo environment. Now, for the pulse beam, there are 3 different ways of pulsing the beam, basically. The first one is on-off pulsing. So in that scenario, or for that type of pulsing, we periodically turn the beam on and then we turn it off again. And as a result, the beam current switches between some nominal current and 0. The second type is current pulsing, which is similar to on-off pulsing, but instead of having a 0 current, we have a lower current. So we're kind of switching between a higher and a low current. Finally, we can do energy pulsing, in which case we change the beam energy between a low and a high beam energy. The 2 control parameters for the pulse beam are the repetition frequency, which is 1 over the period of one pulse, and the duty cycle D, which is basically the ratio between how much time is spent in the high cycle, or like in the on cycle for the on-off pulsing, for example, divided by the total duration of one pulse. Now let's first look into open loop pulsing. So first, on-off pulsing. On this slide, I'm really just trying to highlight the differences between the duty cycle and the frequency and how that affects the beam response, or the potential response to the beam. So the duty cycle essentially determines the converged potential, because the duty cycle more or less scales the electron beam current. We can actually compute an effective continuous current due to the electron beam by multiplying our nominal current, so the beam current when the beam is turned on, by multiplying that with the duty cycle. So if we have, for example, a duty cycle of 0.5, that essentially just results in half the nominal beam current. And the frequency the pulsing frequency determines how much the potential deviates from the average during one pulse cycle. So that's shown on the figure on the right. For example, the blue and the green curve use the same duty cycle, and therefore the 2 lines converge to the same potential. the same applies to the red and the yellow curves. However, the blue and the yellow lines use a lower frequency, and therefore the amplitudes of those oscillations are much larger compared to the green and red lines that use a higher frequency. So the on-off pulsing example here shows that on-off pulsing can reduce the net beam current delivered to the target, and therefore the beam perturbs the target potential less from its natural equilibrium. The reduced current reduces the number of excited secondary electrons and X-rays, which is not necessarily beneficial for estimation methods because we want to have as much signal as possible, right? But at the same time, pulsing may still enhance the signal because we can pulse the beam at a known frequency, and then if we filter out any other frequencies in the signal, we might actually be able to enhance the signal here. Now, second, we could do energy pulsing. So in this case, again, we switch between a low beam energy and a high beam energy. And the low landing energy, shown with the areas in like this blue color, are beneficial for the Electron method. And the high landing energies, shown with the purple areas, are beneficial for the X-ray method. So by pulsing the beam between those two energies, we create conditions that are either at one point beneficial for the Electron method or for the X-ray method. Now, one thing that we can do with energy pulsing as well is to make a open loop charge control better, and that charge control idea was developed in the previous work. So I'm gonna go over this slide really quickly, but in previous work, and I showed those two publications on the top left. There was one conference paper with a recorded conference presentation as well, and the corresponding journal paper shown in the top left as well. Now, what we find in that previous work is that if you hit a target object with an electron beam, there are actually multiple equilibria possible that could be obtained. Now, I'm going to go really quickly over this, but basically this simulation shows that you can either converge to an equilibrium that is kind of determined by the secondary electron yield and how that balances with all the remaining currents in the space environment, or you converge to a potential that results in a very low, basically negligible landing energy of the electron beam. So right here, for example, we use a electron beam energy of 10 keV, and the resulting equilibrium potential for the target object is negative 10 kilovolt as well. So it's basically, there's a very strong relationship between the beam energy that is used and the converged target potential. Now, as a result, because we know that so well, that left side stable equilibrium could be maintained, and the potential is known reasonably well as long as the surface of potential and the beam energy are known. Now, the problem here is that this left side equilibrium results in a negligible landing energy, and therefore barely any secondary electrons or X-rays are excited. Now, as a result, and that's really the main issue here, we don't know if the beam is hitting and charging the target at all, or if it's missing it entirely. Again, if you're more interested in this work with multiple equilibria, I encourage you to watch the previous conference presentation video that we've uploaded, or to read the corresponding paper, especially the journal paper. So one way to deal with that lack of signal is to use energy pulsing. So if we start with a 30 kV beam to achieve a highly negative potential of like negative 27 kilovolts, and we then reduce the beam energy to 20 kV, we achieve that stable equilibrium, that so-called left side equilibrium, that is equal to negative 20 kilovolts. If we stayed there, or like kept using a beam energy of 20 keV, we would have a landing energy of 0 keV and therefore no signal. And we wouldn't know if we are hitting the beam, if we are hitting the target with the beam or not. Now, if we started pulsing the beam with energies between 20 keV and 22 keV, then periodically we have landing energies between switching between either 0 or 2 keV, and therefore periodically we get a signal for the secondary electron methods. And because we get a signal, we can basically confirm that we're actually hitting the target with the electron beam. And at the same time, the electric potential of the target remains very close to the negative 20 kilovolt equilibrium. Now, another way of pulsing the beam, or another way of using the pulse beam, is for closed loop charge control. So the goal here is to control the electric potential to achieve the desired potential of negative 3 kilovolts. And using an on-off pulsing strategy, we want to control the duty cycle that will result in that equilibrium potential. And we do that by using a simple feedback control law. And that feedback controller uses the estimated potential of the target potential. And we do this using a control frequency of 1 Hertz. Now, as we can see, the duty cycle converges to a value of 0.28, and this will result in the effective current that is needed to obtain that potential of negative 3 kilovolts. Now, if we look closer at the figure on the right, we see that the converged potential is slightly more negative than negative 3 kilovolts, but that's because of the simple estimation method that I'm using here to simulate the estimation. What I'm doing here is that I'm always taking the maximum or the highest potential of the previous control cycle as the estimation of the target potential, and therefore the maximum potential, the highest potential, converges to negative 3 kilovolts instead of like the average or so. Now, similarly, we can use closed loop energy pulsing. So in this case, again, we want to achieve the desired potential of negative 3 kilovolts, but now instead of controlling the duty cycle, we're controlling the beam current. And instead of using on-off pulsing, we're using energy pulsing, where we switch between beam energies of 20 keV and 6 keV. We estimate the potential in the same way as with the previous method, and we also use a control frequency of 1 Hertz. Now, as we can see on the right, the potential converges to roughly negative 3 kilovolts, but here the landing energy of the electron beam switches between a very high landing energy of more than 15 keV and a lower one that is about 2 or 3 keV. And now the higher energy, again, is better for the X-ray method, and the lower energy is better for the secondary electron method. So while we're controlling the potential, we make sure that each method has some beneficial parameters given due to the electron beam for some time periods, and we switch between those parameters basically. So in conclusion, pulsing the beam allows to quickly switch between beam settings that benefit one method at a time. Using on-off pulsing reduces the effective beam current delivered to the target, such that the target potential is perturbed less while sensing. Energy pulsing allows to switch between a low landing energy that is beneficial for the secondary electron method and a high energy that is beneficial for the X-ray method. And finally, energy pulsing can confirm that the beam is hitting the target during the open loop charge control method that we've proposed in previous work. If you're interested in more results, I would encourage you to read the papers that I mentioned and also the conference paper for this presentation. And if you have any questions, please feel free to reach out to me per email or on LinkedIn.